Just forget about the password fields, forget the BitLocker warnings and the secure boot logos. Most people, and even some IT professionals, think a BIOS or UEFI password means a computer is safe from physical tampering. They think it's a fortress, but no. To me, your password isn't a wall. It's a temporary delay. Anything I can touch, I can bypass easily, including the BIOS lock. And once I bypass it, I'll own the boot process. I'll boot from my own USB drive, bypass your OS login, and dump your Windows hashes. Or worse, inject persistent rootkits directly into your motherboard's firmware. I'm kidding obviously, but I'm here to show you how it's done. At the end of the video, I'll tell you something important about one project where you can participate if you're really into cybersecurity and IT. Make sure to stay for that. Now, let's log in and let me show you what I know. Give me a motherboard, a few basic tools, and less than 10 minutes. Before you break the system, you need to understand what you're looking at. A BIOS, or its modern replacement, UEFI, is the first code that runs when you press the power button. It initializes the CPU, trains the memory, and hands off control to your operating system. The password prompt you see is essentially a simple logic gate during the power on self-test, or post phase. If the user input matches the stored value, the bootloader continues. If not, the system halts, or the CPU stops calculating data. But where is that stored value kept? How is the logic gate enforced? That is where the vulnerabilities lie. As someone who deeply understands BIOS, I don't guess passwords. I attack the architecture that stores them. Let's start with the lowest hanging fruit. The attacks that shouldn't work, but they absolutely do. Physical SRAM starvation. For decades, motherboards stored your custom settings, including the BIOS password, in a tiny chip called the CMOS, or complementary metal oxide semiconductor. But here's the critical engineering flaw. This specific memory is volatile. It requires constant electrical power to maintain its state. That power comes from the 3.3 volt battery on your motherboard. If I open the laptop or desktop case, I don't need to hack anything. I just need to open the circuit. By removing that battery and pressing the power button, I drain the residual voltage from the capacitors. Without power, the SRAM completely forgets everything it is holding. The zeros and ones literally evaporate. When I plug the battery back in and boot the system, the BIOS realizes its memory is corrupted and restores the factory defaults. The password? It's gone, wiped from existence. However, if you're attacking a modern enterprise-grade laptop, this won't work anymore. Manufacturers realized how weak SRAM was. Today, they store the security credentials in NVRAM, non-volatile RAM, or dedicated security chips. NVRAM does not need continuous power. You can leave the battery out for 10 years and the password will still be there. To beat NVRAM, we have to exploit the manufacturer's own safety nets. This brings us to method number 2, the algorithmic backdoor. Imagine you're an IT administrator for a company with 10,000 laptops. Users forget their BIOS passwords all the time. The manufacturer cannot expect you to replace the motherboard every time an accountant forgets their credential. So, they built a backdoor. When you turn on a locked laptop and fail the password 3 times, the system doesn't just lock up. It generates a system disabled screen and it gives you a code, a string of numbers or alphanumeric characters. This is not a random error code. This is a cryptographic hash generated by the BIOS, usually derived from the laptop's serial number. As an attacker, all I do is take that code and run it through a reverse engineering database. If the laptop gives me a del suffix like 595B, I feed it into the algorithm and it spits out the exact master administrator password for that specific motherboard. I type it in and the system unlocks. It is a mechanism designed for convenience, functioning exactly as intended, but weaponized by attackers. It proves that there is no true zero trust in consumer hardware. There is always a master key. But what if you're dealing with a modern, high-security machine? If the manufacturer disabled the master key, then we stop playing with software. We go straight to the silicon. Method number 3. The absolute undeniable hardware override. Everything the computer knows about itself its firmware, its secure boot keys, and its NVRAM password is physically burned onto an EEPROM chip on the motherboard. This is usually an 8-pin chip communicating via the SPI protocol. I don't need a system to authenticate me. I have physical access, therefore I'm the ultimate authority. I take this CH341A USB programmer. It costs about $10. I open the laptop, locate the SPI flash chip, usually a Winbond or Macronix, and I clamp the clip directly onto the exposed metal pins of the chip. I am now physically connected to the motherboard's brain. The USB programmer provides its own 3.3 volts of power directly to the chip, waking it up while the rest of the laptop remains completely dead and powered off. Using open source software like NeoProgrammer on my secondary machine, I command the chip to dump its entire 8MB or 16MB binary payload to my hard drive. Now I have a complete copy of the target's firmware. From here I have two options. Option A. I open that binary file in a hex editor. I search for the specific hex offsets where the NVRAM volume is stored, highlight the block of data containing the password hash, fill it with zeros, and flash the modified file back to the chip. Option B. I simply download a clean, factory unlocked BIOS file from the internet and I use the USB programmer to completely overwrite the chip on the motherboard. If you need any additional assistance with these, definitely check my BIOS repair video linked above. When I'm done, I unclip the tool and press the power button. The laptop wakes up, reads the new clean firmware and boots directly to the OS. The password is bypassed. If there is one thing you should take away from this video, let it be this. Physical access is total access. If you are defending a network, you cannot rely on endpoint passwords alone. You need full disk encryption and proper secure boot chains. I'm building this channel to show you the exact mechanics of how systems fail, from the hardware level all the way up to cloud infrastructure. Now, before this video ends, give me 30 more seconds because I have something important to share. I'm looking to connect with 10 of the most professional and ambitious people in this community to help me build the largest bug bounty network out there. It might sound ambitious, but I've identified a major gap in the solo bug hunting world that we can solve together. I started a poll on my channel's community tab, so please check it out. Join our Discord server and let me know in the comments if you're in. To conclude, if you want to know how to truly break something, you must first understand how it is built. Now, hit that subscribe button and drop a like so this video reaches more people like you. Thank you for watching and I will see you in the next one. Goodbye.